Mhm. Mm. Well, all right. Hello, everyone. So, um, someone asked about the mini quizzes. I think what I'm going to do is I'm going to basically have like, it's going to be like an online quiz, probably mostly true and false, and then a bunch of like text questions, because obviously few of us are in different time zones, so I'll have to make it like asynchronous. So probably like Wednesday, anytime on Wednesday. I'm thinking something like half an hour on, I think I'm probably just gonna stick to the topic of topic models, because we've obviously covered a lot of stuff and given you quizzes on those topics, but yeah, so I need to decide. But I think topic models is sufficiently complicated that there should be a bunch of questions I can ask, and obviously I can't make it closed book or anything, and I'm not going to bother trying, so it really is more just for your own sake, just so you know what you know, and it's like worth like 3% or something, so it's really not that big of a deal. Okay, so just mainly the purpose is just to keep you on your toes, and yeah, I will send out a final thing tonight. Okay, so it's been a long time, but I hope we can get through. We'll definitely get through topic models today. Famous last words. And hopefully we can get on to language models. I mean, we sort of got a lecture back because we don't have to do the midterm, so I'm not too concerned. But yeah, so topic models, I said, is actually a lot of sort of different parts that comprise of the whole thing. And so we're at sort of the final step, and then we'll move on to language models. Okay. So where were we? Right, okay. So this is where we left off last week. Let's see. Right. Okay, so there's a lot of magic that happens in the previous slides. I think the most important thing to understand about this is that Okay, so remember what we're trying to do is we have this general model, which is equivalent to looking at some joint probability, right? So I'm gonna draw it out. Betas, Zs, and Ws, right? And really what we're looking at is we're gonna look at the posterior, right? So we're trying to understand this posterior. And so we're saying, okay, so we can't actually access this, we can't actually calculate it, so we're going to do some Gibbs sampling. And then some magic happens. Turns out all we need to do is basically sample each individual Z, and then you sort of do the Gibbs sampling just on the Z chain, right? So it's as if you could just forget about everything else and just focus on the Zs. And that's basically the Gibbs sampling procedure, right? So you have your Zs and you want to sample from the Z distribution. You want to understand the distribution of Z. So you're going to basically do Gibbs sampling on every single element of ZDN, right? So I'm going to try and be more explicit, right? Okay, so in this example here, right, this guy is Z, sorry. This guy is Z11, this guy is Z12, this guy is Z13, this guy is Z21, Z22, Z23, right? So what the Gibbs sampling procedure is actually going to do is that you're basically going to sample these and then just keep going, right? So remember what the point of Gibbs sampling is. I want to understand the joint distribution of some random variables, but I'm going to just do the conditional, I'm going to sample conditionally and sort of iterate through every single one of them. Okay, so what does that do? Well, ultimately what happens there is, remember what's the goal of Gibbs sampling is to create the distribution. So once I have that distribution, I can then sort of estimate the joint distribution of these Zs, right? But actually, that's not actually what I care about, right? I don't really care about the Zs, right? So what do I care about? The two things I actually care about are the things that are not even being, the two things that are not even being sampled. The things I care about are the thetas and the betas. Right, so what are the thetas here? Thetas correspond to topic proportions in a document, right? And the betas correspond to the topics themselves. Okay, so these are actually the two things that if you think about, well, now that you've done the homework or doing the homework, you think about the output of topic models, those are like the two things that come out of it. I don't care about these topic labels so much. Like, I wouldn't call them nuisance parameters, but they're sort of on the way to what I really care about, which are these two parameters themselves, right? So we'll see in a little bit how we can get these thetas and betas, but that's something just to keep in mind, that it sort of seems like a very roundabout way where we're actually going to sample the Zs, right? Not actually sampling these things that we care about, but you can actually figure out the posteriors for the thetas and betas through this process. Okay, any questions about that before I go and describe this formidable equation? Okay, no question. Hopefully people listen. Okay, so it's almost like at this point, let's just, like, for now, let's just forget about topic models. Like, how does this even relate to topic models? I just want to describe the procedure of this sampling. Okay. So remember how this works is we're basically conditioning on one of the Zs, indexed by DM. Sorry, we want to sample from this ZDN, conditioning on every other ZDN, right? Every other Z variable. Okay. And obviously we're also conditioning on W because W is the data. So that's what we see, right? And so what I said here is that you should think of WT and DT They stand for, the W stands for word, T stands for topic. So it's a word topic table. D stands for document, so document topic table. Okay, where did I draw my document topic? Okay, so actually let's go and look at this example. Okay, so I'm just gonna give you, I'm gonna sort of go back and forth here. Okay, so this is the particular document that I have, right? So the point is that, you know, when you do these Bayesian types of analysis, you're going to start with some initial value of your Zs, right? Or this just could be at any state. This is your current belief about your current choice of Zs in your sampling procedure, right? So the Ws are the words, and you have 3 different documents, okay? So what am I going to do? The first thing, basically, in order to do this procedure, the way I'm going to do this is I'm going to first create my document tables and my word tables, right? So the first step, I just want to create these DTs, right? I mean, it's a little bit big, but let's go through this. So it's going to be play, games, oops, nope. Sorry. This is 1, 2, 3. So these are the documents. And on the top side, I have 1 and 2. Right. So we did this last time. So this is document 1 has 1 of this, 2 of this. This has 2, 1, and 2 and 1. Okay. So this is just the procedure of creating DT, and WT is the more ugly one, right? So this is topics 1 and 2, and now we have play, games, soccer, range, golf, audio. Okay, so here I'm creating my word topic, right? So I want to see play is seen 3 times in topic 1 and 0 times in topic 2. Games is seen once in topic 2 and 0 in topic 1. Soccer, the same. Range is 1 each. Golf is 1, 0. And audio is 0, 1. Okay, so this is just sort of brute force, very simple. And last time I hinted at why these DT and WTs are, are the key tables we want. And the point is that if I were to give you this instance of my data, right, how would you estimate the thetas and the betas? Well, this would be exactly your empirical counts, right? So if you think about it, this guy here would basically sort of be like your beta hat 1, right? Because that's exactly the empirical count of the number of times a word was in that topic. Obviously, you have to normalize, right? Because it has to be a probability distribution. And then for my theta ones, well, that would just be my theta 1, right? That's the empirical frequency of which topic is in which document, right? So these DTs and WTs are essentially what you're doing is calculating empirical frequencies of the parameters that we were interested in. Okay, that should be fine, right? No questions here. Okay, so this part should be pretty straightforward. So then the question is, well, okay, what do we actually do with this, right? So the first step is always just to create DT and WT. Where are we going? Oh, sorry. Let me just delete this guy. Yeah, that's okay. I'll just leave this here for now. Okay, so then what am I saying is what I want to describe the distribution of ZDN, right? And this distribution is given by this big formula here. Okay, so how does this work? Basically, the way this works is my probability that this particular ZDN. So for now, let's just pick ZDN. We're going to pick Z11, right? So I'm going to pick D equals to 1 and equals to 1. Okay, so I'm saying the first word in the first document, I want to sample this again, right? And I want it, what's the probability that it's going to be equal to kappa? Well, it's proportional to, right? This proportional to is very important. It's proportional to basically reading off these values from the table, okay? So the first thing you need to be careful about is, what do these things mean? What this means is that basically I forget about the influence of that particular variable that I'm now trying to sample from, right? Intuitively, you're thinking about like, I'm conditioning on all the other Zs, right? Since I'm conditioning on all the other Zs, that's what I use when I am doing the calculated probabilities. So I shouldn't look at the current influence of the current value of ZDN, right? The current topic that ZDN is, because I'm now creating a new one and I'm not conditioning on that, right? So what am I saying here is that I'm trying to now sample, I'm trying to sample a new Z here, right? And I condition on all of these, right? So in particular, to be more precise, I'm saying, what's the probability of Z11 equals to kappa given all the rest, right? Minus 1, 1, right? In this particular case, this guy is this. Oh, sorry. This guy. Oh, and that should be a conditional one. All right. So, you know, since I'm trying to calculate the probability, I shouldn't use this count when I'm creating my documents. So that's what the negative minus dn basically stands for, right? What that means is I'm going to basically create my document topic and word topic tables without this play guy, right? So in this particular case, that means that this is going to be 0, and this is going to be 2. Okay, so this new thing is the minus dn if I place 1 with 0, and minus dn if I place 3 with 2. Okay, so this is just, and then here you're literally reading off, right? So I have my wt minus dn, and I have the nth row and the kappa column, right? So that's this guy here. It's the nth row and the kappath column. Here is the dth row and the kappath column. Okay, so you can basically read out you can just basically calculate this expression by reading off from the table. Okay, but one thing is important is that, as I said, this is proportional to statement, right? So just to see if people are following, who can tell me how I would figure out what's the proportion here?
You could sum over all the k's, maybe.
Yes, exactly. Yeah, so exactly. You would just sum over all the kappas, and that would get you your probability distribution. Yeah, nothing fancy. So this, okay, so this interpretation is sort of what I was getting at before, which is that if you look at this left-hand guy here, and you look at this right-hand guy here, this basically word topic table corresponds to what we saw already, which is the betas, right? This corresponds to the thetas, right? So what you're sort of seeing is that it's sort of like looking at the probability of the words in topic kappa, and you multiply it with the probability of topic kappa in your document D. But really, I think the other way to think about this is that this is just looking at the empirical counts, right? If you think about this, this is the empirical, these WTs are the empirical counts for your betas, right? And then what you do, we'll see this when you look at language models. This is basically like a smoothing parameter, right? And you saw this with the Dirichlet distribution, right? If you think, you remember what the Dirichlet distribution is, it's like the posterior mean for the Dirichlet distribution. One intuitive way you can think about the posterior mean is that you have your MLE, right, which is the sort of empirical frequencies for the counts, right? Okay, sorry. So let's think back about what this whole Dirichlet multinomial thing is, right? So you have this conjugate pair with the Dirichlet multinomial, and your goal of this is you want to figure out what were the probabilities assigned to your die, right, to the faces of your die. You want to understand the probability assigned to your faces of your die, and you have your prior, which is your Dirichlet. That's your prior belief about what the probabilities are. And then you have your data, where you actually are flipping your, not flipping, you're rolling your die, and then you have those counts, right? And then you have your posterior, which is basically a mashup of your prior and your data, which you can think of it as your maximum likelihood estimator, right? So I guess I should, again, be a bit more precise here, right? So let's say I have a 6-sided die, right? And I see, so, I see counts, let's say like 100, 200, 150, 10, 30, 60, right? So I'm rolling this die. This would be the, if I wasn't a Bayesian, I would just look at sort of, the actual frequencies of this, and this would be my best estimate for the probabilities, right? I would take each value here, obviously divide by the sum, and that would be my estimate for the probability, whatever, let's say the same sum up to n. My estimate for the probability of landing on face 1 would be 100 over n, right? And so that's basically the same thing as this expression here. You can look at it, you can look back at, you sort of like decompose the table, but that's basically the same thing. I'm fixing a particular k, right? It's kappa, sorry. Right, so WT, we go back to WT, I'm basically fixing one of these columns, and I want to estimate beta kappa, right? What this sort of tells me is that this basically gives me the empirical frequency for the nth word n, right? So it's basically like this, right? So I have the 6-sided die, I have these empirical frequencies. From there, I can estimate my probability, which is sort of the MLE, right? But remember, we have my prior, right? And so the way this actually works is that the prior basically ends up corresponding to basically adding like an alpha plus 6 alpha here, right? So what that essentially does is that basically it adds alpha to every estimate. Right, so that's the influence of the prior, and in the base notes, I think we go over this a little bit. Okay, so this is sort of the one way you can think about this, and as I said, this will be important when we look at language models. When we think about this, is like it's like a smoothing of my MLE, right? The key point is that if this guy was 0, if he had 0 counts, then that would mean that I would never, my guess for the side 4 to land would be 0. But now, because I have a plus alpha there, I can at least give you some probability of landing on side 4. Okay, so if that didn't make sense, just go back to the base notes. It should be at the end there. But you should sort of see that this is very similar to what this guy looks like here. So this actually turns out to be basically the posterior mean for this type of Dirichlet multinomial, where your eta corresponds to the prior that you put on the original Dirichlet. And the same thing holds for this guy here. Okay. Okay. Questions? Yeah, so at some level, it's really just, this is just a formula. You plug it in. This is literally what you would do if you were to manually do give sampling by hand. In the midterm, usually I get people to do this, like manually do it by hand, because I think it's sort of informative to see actually how this process works. And you know, maybe in the quiz I'll get you to do it. Okay, so yeah, so then literally you just read off, you know, for instance, you know, something you should do at home, and maybe I'll send the solution later, is just like figure out what this probability corresponds to for this particular toy example. I'm not going to do it because I don't have much time left for talking models, but yeah, you should be able to do that. Okay, so let's try and recap like all of topic models in sort of a very quick manner, and sort of see where everything fits here. So ultimately what we have, I'm going to repeat myself, set of documents. I want to do classification. I want to basically extract topics. You know, I want to classify each document into a particular topic, into a set of topics that corresponds to the thetas, right? And a nice side product of this is also I can extract what the topics themselves mean, right? Set of topics is the betas here. You see in your homework that you have to actually interpret these betas, right? These betas adjust the probability distribution over words, and usually what you do is you look at the top, 20 probability words, and then label it with some human understandable topic, right? So you set up this Bayesian model, right? This is a very general model that involves sort of multinomials and Dirichlets, and it's quite a complicated setup, right? And then what you're going to do is you're going to basically be a Bayesian and try to calculate the posterior given the data. The key point is that you can't actually do that in a closed form. So what you're going to do is you're going to estimate you're going to give sample only on the Zs themselves, right? And so that's what this step is. Here I've described to you how to do the give sampling. Okay, so in particular, how would you do this? You would initialize with some random set of z's, right? So in this particular case, you could just set all the z's to be 1, or you could just like randomly sample your topics, right? So you start with some initial value of your z's, and then you just run your chain, right? So what does that mean by running my chain? I would basically, I know what the forms of these conditional probabilities are. That means I can basically, sample from them, right? So I'm going to sample this Z11. This could either give me a 1 or could give me a 2. Let's be, yeah, so maybe it's 1 again, right? Then I move on to the next guy and I can sample it. Maybe it now becomes 1. And I move on to the next guy, let's say it's 6 to 2. And you just keep going, right? And you keep doing this forever, for a very long time, right? And this procedure follows the whole Gibbs sampling procedure, right? Where I basically condition on every other variable and I sample the current variable, okay? Then the question is, well, how do I extract the thetas and the betas that I actually care about? So what actually is going to happen is, while you're doing this whole Z thing, right? While you're doing this Z procedure, what you're actually going to do is you're actually going to keep track of these DTs and WTs, right? Because it turns out that these DTs and WTs, if you read off these theta hats, these are your actual samples from your thetas themselves. So because it turns out that Zs are sort of a sufficient statistic for your thetas and your betas. And so in a nutshell, what you're actually doing is you're running the Z chain, but the key thing you're keeping track of, well, in addition to keeping track of what the Zs are, what you're keeping track of are the DTs themselves. And these, this is theta 1, theta 2, theta 3, right? And then you're just basically going to look at the means of your samples for these, right? So what you could do is you could basically, sort of store theta 1, so store this particular row every 100 iterations. And then you just take an average of your theta 1s, and that would literally be your posterior mean estimate for your thetas, and the same thing for your betas. Okay, so after all that, that's how you get your thetas and your betas, which correspond to, as I said, this thing we see when we actually run these algorithms. So we've finally, hopefully, have come full circle to explaining how these topic models are able to extract these parameters of interest that we care about. Yeah. Questions? Okay. Yeah, this, oh, the context of Gibbs. Right. So the, okay, so there's a little bit of magic that I'm not going to go through, but sort of, okay, so the idea is I'm trying to calculate the posterior, right? What is the posterior again? That's literally just these thetas, Zs, beta given W, right? And the reason why I'm doing this is because I'm just being a Bayesian about it, right? I have my data, which is W, and I want to calculate, I want to figure out the distributions of these latent variables so I can then look at the posterior mean, and that will be my sort of estimate for the parameters of this model, right? And the point is I can't do it, so there is some magic that tells me that I actually don't need to calculate this joint posterior, like this joint distribution. All I need to do is sort of look at the probability of z's given the w's, right? So I sort of like I integrate out the thetas and the betas by some magic, right? And so now what I'm saying is all I need to do is understand the distribution of the z's, right? And so this is the step where we do the Gibbs sampling. You can sort of think of this is the Gibbs sampling step, right? Because remember, with Gibbs sampling, I basically have a set of I have a set of random variables I want to understand the joint distribution of. Here, these are the z's, right? In this example, these are the labels, the 1, 2, 2, 1, 2, 2. So I'm going to do the Gibbs sampling procedure where I just sample one of the z's at a time, conditioning on the rest, and with all the caveats that I said in the class where we talked about Gibbs sampling. You want to, do some skipping, or you also want to do you don't want to start with your initialization because obviously it depends on the initialization. Eventually, you can basically estimate a somewhat independent sample of my z's, right? But in actual fact, that's not even what I care about. Like that's sort of the, I'm doing that in service of the fact that actually for a given set of z's, I can then estimate the thetas and the betas just by reading off the table dt/wt, right? So it's really a roundabout way of getting at the true parameters that I care about. I'm sort of sampling the z's, and I'm sort of searching through that space and figuring out what the joint distribution of the z's look like. But in the process of that, I'm actually doing the same thing for the thetas and the betas, right? So this Gibbs sampling procedure is understanding the joint distribution of the z's. But in that process, you go through and also get the thetas and the betas. Okay. So hopefully that was a bit clearer. Can you explain how the Gibbs sampling update step works? What is the update step? Okay, so I mean, okay, so basically what this is okay, well, I've written a lot on this and I don't want to throw it away, but let me just rub some stuff out. Okay, so again, with Gibbs sampling, you're doing this conditional sampling, right? So I want to resample this guy, which is Z11. Okay. So this would be one of my new Z11s. If I do it, if I do all of them, that will give me a full joint sample, right? So in order to sample from this, I need to know, well, this is a multinomial distribution, and there are sort of two things I really care about. It's PZ11 equals to 1 and PZ11 equals to 2, right? And in order to do that, I literally just read off from this equation. And sort of the key point of this equation is that it's looking at these word topics and document topic tables, which are sort of the empirical frequencies of what you care about, except you get rid of the influence of the current variable that you're trying to sample from, because obviously that doesn't play a part now because you're sampling that variable. How does beta and theta then ultimately depend on the eta and alpha parameters that we set? Well, so here you can see where the etas and alphas come in, right? So as I was saying, the intuition for this is you have your empirical counts that you've sort of figured out when you're doing the sampling. And then these prior parameters correspond to smoothing out your frequencies, right? So that's going to affect your estimates for beta. That's going to affect your beta hats and theta hats. And so, yeah, that's really where the influence of the prior comes in this particular case. Okay. If there are no more questions, we'll move on to the next topic. Yeah, I mean, last semester I did like a recap where I went through the whole thing again, which is sort of helpful for people. But I probably won't do it this time. Yeah, I feel like we've spent quite a while on this. I mean, I've sort of glossed over some subtleties here and there, but for the most part, I think, well, I've definitely spent more time on this than most times. Okay, so let's get on to language models. So I think language models are actually a lot of fun. They're whenever I sort of introduce machine learning or the NLP side of things, a lot of the things we sort of showcase are based on language models. So it's important to understand what they are. Okay. Any questions? Cool. Okay. So we're actually going to go through this a little bit slowly. Well, slowly. I'm going to sort of, it's going to take a while before we get to sort of the state-of-the-art language models. Well, I wouldn't say state-of-the-art, like sort of the fancier language models. And it will help to sort of start from scratch and be a little bit sort of slow about introducing this topic. Okay. So this first part will be a little bit participatory. So obviously, well, a lot of you, I assume, are using these these AI assistant type things where they're understanding what you're saying, interpreting it, and then actually, giving you a response. So let's try and think about how intuitively what's going on here, right? So in particular, all I care about in this part, right? So obviously Alexa, there are many things going on, right? You have your audio signal where you're speaking to this machine, right? Then the audio signal needs to be converted to a digital signal that needs to be interpreted into text, right? Once you've converted into some text that the computer can understand, then the computer needs to understand the text, right? It needs to then, give a response and then convert that response into an audio signal, which then gets fed back to the speaker. Okay, obviously there are several other parts. The part that I want to focus on here is just the part where I'm looking at the conversion from the audio signal to text, so speech to text. Okay, so how does this work, right? What happens at some high level is I have some audio signal, right? This is some audio waveform, right? And what I want is to get back like, I like hi. Okay. So suppose, okay, let's give me a more contrived example. Okay, so suppose I have these suppose I have these word forms, these audio forms, and I've interpreted, like, let's say the first few portions of this, and it says, oh, well, okay, let's make it even more extreme. Suppose the first set of this signals, I've already interpreted that, and I've guessed it to be Yale. Okay. Now I'm going to interpret the second portion of the signal, what's going to happen? Okay, so naively, like what you're going to do is you're going to basically look at this signal and figure out what is the most likely word that this form represents, right? But clearly here, okay, I'm not going to ask the question because I think I've already given you the answer. Clearly here, the way I've set this up, right? This audio form in the second part, right? Not only should you use the fact that you can sort of, you have this signal here, right? This is the signal. But you should also use the fact that the previous word was Yale, right? So in fact, anytime you're doing this type of speech to text recognition, right? When I first thought about this, like it sort of blew my mind. Like when I think of speech to text, I think of it as just literally that. Like you have these audio forms, and you're just basically matching audio forms to words, right? But it actually was pretty obvious the way I've set this up. Like not only should you match the form to the word, but you should also take into account the fact that, well, this next word is probably not universality or something, right? Right? Maybe it's universality or university, right? Maybe if you just consider the signal of the audio form itself, you would guess this to be like 0.3, and this would be 0.2, 0.03 or 0.029, right? If you didn't have, if I didn't tell you what Yale was, if I didn't tell you the previous signal was Yale, you would just guess universality, right? But if I know the previous word is Yale, and these two are pretty close, independent of the previous signal, then if I give you this previous signal, then obviously you should upweight the second guy, right? So language models is basically the idea that you want to understand what's the joint likelihood of words in a sentence, right? So this is sort of a surprising, at least to me, it's a surprising application of this idea of sort of understanding which words, like sort of which sentences are likely to appear together, right? The more classic approach, the way you usually think about language models is literally like this, right? This is sort of the smart Gmodel compose, where I literally have a bunch of words in a sentence and I want to just fill out the rest, right? How am I going to do that? I'm just going to, well, I'll just have a set of candidate sentences and I figure out which is the most probable given the previous, sentences, essays, your predilections that you have, right? So this is a very typical case of a language model, right? But as I said, you also use language models in any case where you're trying to interpret something into text. You can also use a language model there. Questions? Does that make sense? Okay, so I'm going to be a little bit more precise. So what are language models? It's literally, intuitively, it's just saying I want to have some numerical hint as to which types of sentences are more likely than others, right? Really what I'm doing is I'm assigning a likelihood to a sequence of words, right? So in this particular case, I have n words and I'm going to assign a likelihood to it, right? Later on, we'll see that this factorization obviously becomes important. Okay, so the thing I was just describing was this, one way you can use this language model is through this source channel framework, right? So you basically treat, this is sort of you're creating words, right? These are the words you're creating. And then this is your vocal cords, right? So this is you're creating words. And then this is sort of your vocal cords, which creates an audio signal. Right? So in order to figure out what the words were, you want to take advantage of your knowledge of sort of the words, as well as the probability of a particular signal given the word, right? So it's not, so the key point here is that like when I'm creating words, usually when I think about sort of speech to text, well, suppose I only give you one word at a time, right? I want you to translate, not translate, I want you to create, I want you to figure out, I want you to like, what's it called? Like dictate, is it dictate? No, I forgot what the word is. Okay, I want you to figure out what word I'm saying. If I do this one at a time, then basically I can't use, I can't use a language model because I'm only giving you one audio form at a time, so I can't take advantage of that. So then that would basically all I would do is I would just focus on this guy here. Well, actually, even if you had one word at a time, you could still use your language model, because then you could figure out, well, which words are more likely to be spoken, right? So you would also actually, even if you had one word at a time, you would still be able to use this language model. But sorry, okay. Anyway, so this is sort of the formal notion of what I was trying to describe, which is the fact that if I'm doing any sort of conversion from audio to text, not only do I want to just do that conversion just as well as possible, but I also want to take into account the fact that I actually understand which sentences or which collections of words are more likely to be together or not. Okay. So this is used in basically all sorts of NLP applications. So language model is not just about creating language, given text. It's any type of time when you're doing some conversion into text as well. Okay. All right. So what we have is we have a set of, think of it like a corpus, right? N could be like a million, right? So what is my corpus is some set of words here, and I'm going to assign a probability to this sequence of words, right? Clearly, what I can do is I can basically do this type of conditional, sorry, I can do this decomposition, right? This is just by definition. So as n grows, though, this is not going to be particularly nice, right? So, imagine, right? So suppose I'm looking at some essay where I have like the, let's say like the 1,000th word is, well, okay. So I'm trying to look at the 1,000th word, right? And in order to figure out the likelihood of the 1,000th word, I need to look at every other word before this current word, right? I mean, in some sense, this should be true, right? Because if you think about writing an essay, the probably like your belief about what the next word is going to be is literally a function of all the words you've had before this article, right? But obviously, this is the most extreme way you could do this, right? So let me just work through these parameters here. So the number of histories here is going to grow as the size of a vocabulary to the power n-1, right? What does that mean? Well, this is just looking at the possibilities, all possible combinations of W1 to Wn-1, right? Remember, a word is going to be just a word could be anything from my vocabulary, which is the size of V, right? So in order to fully characterize this probability, well, in terms of the histories, right? The things I need to condition on, I need to condition on the possible things that I need to condition on is size of v to the power of n minus 1. Right? Then, if I look at this guy, what is actually the number of free parameters in this conditional probability? So I'm just going to work through this, right? So if you think about it, what's happening is for each wn for each set of w1 to wn minus 1, probability of wn given, right? For each set of possible w1 to wn minus 1s, right? So for one particular history, I want to figure out what's the probability distribution for my wn. Well, what's that? That's just going to be, I'm going to have v minus 1 parameters, right? So for fixed w1 to wn minus 1. Right? Why is that? Because this is a probability distribution over your vocabulary, essentially. Right? So basically, I need v minus 1 because once I've defined v minus 1 of the probabilities, the last one is just 1 minus the rest. So I only have v minus 1 basically degrees of freedom, right? So for fixed w1 to wn, right? For each possible w1 to wn, this would be the number of parameters that I would have, and then this is just for a fixed history. So then obviously, for all histories, I would have to basically get this total number of parameters, right? So this is clearly not particularly feasible, right? As my n grows, my number of parameters of my model is going to be growing exponentially as a function of the size of my data, right? So then the question is, how do I sort of simplify this model?
You just cap and just look at the previous, say, k words or something.
Yeah, exactly. Yeah. So I mean, yeah, it seems a little silly to actually look at all previous words. All right, but if you want to be pedantic, like you should be doing that. Like if you think about the way we, if you were to have a question where I give you some text and you want to guess like the next sentence, you would have to read the whole text maybe to guess the next sentence, right? But in practice, like we don't want to do this because there's just too many parameters. So then the sort of the obvious thing to do is just to basically sort of do a capping procedure. Okay, so so there's an intermediate step where you can basically say, I want to sort of simplify. I don't want to do w1 to wn. So okay, let's just forget about this. So essentially, you're right? What I'm going to do is instead of looking at all w1 to wn minus 1, I'm just going to pick the last k of them, right? So this is what this theta n is basically saying, is I'm just going to say, instead of looking at all of w1 to wn, maybe I just want to pick the last one, right? So what does that mean? Basically, that means that my wn given w1 wn minus 1, I'm actually just going to replace that with p of wn over wn minus 1, right? So intuitively, that's saying that my language model, I'm going to simplify my language model. I'm not going to actually care about the full history. All I'm going to do is going to look at the previous word, for instance. Previous word seems a little bit crude. So we could, let's look at, instead of the previous word, let's look at like the last 2 words, right? Yeah, last 3 words or something. Okay, so here, a trigram corresponds to looking at the last two words. A bigram corresponds to look at the last word. A unigram would basically correspond to looking at no words, right? So that would basically be equivalent to an independent model, right? But, I assume people have heard, okay, sorry. Some people maybe have heard of what is known as Google Ngram. And this is basically what this is, right? Basically, Google sort of, devoured all of the libraries of the world and sort of, has all this data. And then basically all they do is they basically match these Ngrams and then use that as like statistics when they're, doing their analysis. But here we're going to sort of, for now, just focus on these bigrams and trigrams. What am I saying? I'm basically saying that instead of looking at the full history, right? If I were to be proper, this is an equal sign, right? If I were to figure out the joint likelihood for this set of random variables, I should do this, but I'm not going to do it because it's a bit extreme, and it corresponds to an explosion in the number of parameters. So I'm essentially going to replace. I'm going to get rid of all the other. I'm only going to look back two variables. Okay, so now this is nice because now my parameters is going to grow at a much lower order, right? So it's much more reasonable. No, okay. So that's just, so that's basically the simplest thing you could do. Now we have to think about, well, how do we estimate these parameters, right? So suppose I assume that all I care about in terms of this joint likelihood is just these decompositions. I care about the previous word. Well, I still need to figure out what those probabilities are, right? I still need to understand what this PW given W minus 1 is. Like, how do I specify this, right? And so this is where I was saying it's going to be very similar to the thing I talked about with topic models. You're basically going to just use your maximum likelihood estimate, which is your empirical counts, right? I think that's how you do it. So here we're saying, suppose I have two words, let's say W1, W2, W3, let's say, I'm really bad at, okay, this is not a good example. Whatever, I panicked. So suppose I have W1, W2, right? And I want to figure out what's the joint. Well, I figure out my probabilities for W3, right? This is saying what weight should I assign? What probability should I assign to each vocabulary given the previous two words was this is, right? So what I'm going to do, I'm literally just going to look at my corpus of text and then like look for the the phrases this is, and then figure out what the next word is, and then just take that count, and that's going to be my MLE estimate. Right? Very straightforward, very simple. Okay, so this question may be obvious because I sort of answered already. What are some problems with this model?
Wouldn't one problem potentially be that the context would matter? Like if you're emailing someone, this is might have a lot of different words that you would want to attach versus like an encyclopedia.
Yeah, sure. Yes, that is yeah. So I guess one way you could also think about this is, okay, so yeah, context is sort of like a side information type of thing where you're thinking about like the location in which you're writing this stuff. So yes, actually that seems pretty tricky. How do you even solve that? I think a surrogate for that would be just saying, really what you're trying to say is like, let's, the probabilities here are going to be affected basically by the context, which is similar to what the previous words were. Like, maybe the previous words, like, if the first words were like dear something, something, comma, then that would suggest it's an email, blah, blah, blah. If it's like, Wikipedia, there's the word Wikipedia then, then you could, maybe guess that it's more Wikipedia. So yes, I think that's a hard problem. I think there are easier problems with this model though. And I sort of hinted at it when I was talking about topic models. No one? I should be like John and like just wait until someone says something, which is like something to take like 2 minutes. But I think I would die. Yeah, okay, so right. Whoa. What if count W1, W2 equals 0? Yeah, so okay, so the part of the point here is that, yeah, basically, if you don't have the particular counts, like if you just don't see particular words, then you're basically not going to have, you're not going to be able to calculate these maximum likelihood estimates. So, I mean, so the first thing is, well, if in my corpus, right? So think about what we're doing. We have a corpus of text and I want to basically figure out a language model, right? So in my corpus of text, I should just generally just think about it as like Wikipedia. That's sort of the go-to. Right, so I have my whole set of Wikipedia and I want to sort of figure out this language model. I'm going to learn a language model from Wikipedia, right? From the way people speak on Wikipedia. And, suppose there is no sentence that is, this is bonkers, right? So there's no sentence that actually has this sentence. Sorry, so nowhere does a sentence appear on Wikipedia, probably for good reason. But what that means is that you would, in your estimate for this, if you were to build this language model and then try to estimate the probability of seeing this sentence, you would have zero prediction, like you would predict this with zero probability, right? Because the count for here would be equal to 0, right? Because you never see this in your data, so you don't believe this is a valid sentence, even though, okay, not a great example, but even though you should be giving this some probability, right? So okay, and an even more pernicious problem is, well, actually, what if like this count is 0? I mean, so there you sort of have a weird problem because you 0 divided by 0. Obviously, if count 1, 2 is 0, then count 1, 2, 3 is obviously going to be 0 as well. But so it's the same issue, right? So you don't want to set this up in such a way that you're going to assign 0 value to sentences that you just don't see. Okay, which sort of makes sense. Oh yeah, okay, and the example that like what's his face Chomsky gives is like, well, now it's no longer a valid example because everyone uses this sentence all the time, but he's like, this is a sentence that has, right, okay, so I will get back to that in a little bit. Let me just finish this point. This is an example that he gave of a sentence which is like, it's a valid sentence. It's no one has ever said it before. And so if, you have, very often you can have sentences that people, every now and then people are making sentences that no one's ever said before. I think there's a subreddit dedicated to this where sort of like, I think it's like /r/new sentences or something. But the idea is that, yeah, you shouldn't use your empirical counts for sentences to inform your probability for what you think the likelihood of seeing a particular sentence. Okay. So you can read through that. Okay, so actually, I'm sort of gonna skip this. This part, this is not particularly important. You can read through this. This is sort of an example of how you can get back this is basically an example of how you can sort of get at this issue where you have 0 counts. The key point is essentially what we were saying before with this LDA plus mononomial with the posterior, right? What you're going to do is you're basically going to do a smoothing procedure where you just assign every single event to some small probability, right? So essentially what you're going to do is you're just going to basically so one way to do this is just like, plus lambda to all of these things, right? So that's one way you could just like smooth it out such that you don't have to worry about these 0 counts. You give everything at least a small probability. Okay, so this was when I was saying this, we're going to talk about this in language models. This is the way to fix this, right? If you're looking at just the maximum likelihood estimator, which is equivalent to the empirical counts, a lot of times you won't see sentences, you won't have sentences that appear, but you still want to give it a probability because it still is, a valid sentence. So one way to do is just like add some like small token probability to it, so that it's not 0, right? If you set it to 0, then you're never gonna believe that sentence is true. If you set it to lambda, then it's fine. Okay. So I'm not gonna ask questions. Other ways you can do this, right? You can set this up such that it's like a linear combination of like the smaller probabilities, right? So instead of saying what's the MLE for W1, W2, W3 appearing, that's gonna be a function of the empirical counts of seeing 1, 2, 3, plus the empirical counts of seeing, 3 given 2, and there's empirical count of 3, right? So in the example we had before, forgot what the example is. I guess this is, right? So this is pi given this is this is pi given this is pi, right? So you could sort of like estimate it as like a linear combination of the smaller n-grams. Okay, so here, because you include this guy, then you're sort of guaranteed to not have issues of like 0. Okay, but obviously this is like really crude. It's not very nice. We can do better than this, right? Okay, so how are we going to do this? This is sort of like the step 1 to getting to like really cool neural network style language models. We're going to do something that's a little bit similar, but basically it revolves around this intuition, right? The idea is that each of these sentences are essentially exchangeable, right? Suppose I wanted to figure out the probability of like this sentence, but I only saw these 4 sentences in my data set, right? If I were to just look at empirical frequencies, right, then I would assign this probability to this first sentence probability to 0, right? Even though I've seen these 4 sentences and they're basically like synonymous, right? The fact that I see these 4 sentences should tell me that this sentence is pretty likely, right? Why? Because, well, these cat and dog are somewhat exchangeable. If a cat is walking, then maybe a dog is walking. If a cat is walking, it's probably also running. A bedroom is just like a room, right? So the idea is that you sort of want to relax your, right now when we're doing these maximum likelihood estimations, we're like very stringent about matching the words exactly, right? Like I need to see, like, in order to figure out what's the probability of seeing bedroom, I need these last 5 words, 6 words to be exactly the cat is walking in the, right? But, if I replace cat with dog, then that should still help me, that should still be useful in estimating the probability of seeing the word bedroom, right? So really what we're getting at here is that like it's, I mean, essentially it's like it's like synonyms, right? Sort of like the fact that you have these synonyms, obviously they're not exactly synonyms, but so there's like a more general idea of a synonym. You should be able to relax your notion of what matches, like when you're doing these, essentially what you're doing is you're counting examples of things, right? You're looking at empirical counts. But I actually want to relax what a match is going to be, right? Instead of saying I want to match exactly the words the cat is walking in the, right? Then I'm gonna basically just match words that are like the cat is walking in the, right? So what that means is essentially what I'm going to do is I'm going to basically look at this class-based model, right? So in particular here, let's just focus on bigram, obviously extends to trigrams, n-grams in general. Right, what is this model? This model basically says, instead of looking at just the empirical frequencies of pairs of W1 and W2, what I'm instead going to do is I'm actually going to decompose them, this probability, into looking at the classes themselves, right? So, you should think of this class like, so if W2 was dog, and W1 is like, no, let's look at like dog house, right? So like class 2 is house. So the class of house, corresponds to a set of words like, house, maybe roof, probably abode, blah, blah, blah. The class of 1 is just a group of words like, that are similar to dog, like dog, cat, mouse, blah, blah. Right. So basically what this is doing is this is sort of relaxing your notion of a match, right? This is like, I'm going to basically figure out a clustering for the words in such a way that I can sort of take information, from like other examples of sentences. Okay, so how am I going to do this? Okay, I'm just going to finish this slide and then we'll call it a day. How am I going to do this? Intuitively, what we're going to do is like, obviously pick words that are very, very similar. The way I'm actually going to do this, I'm actually going to build the classes at the same time as I'm building my language model, right? So what do I do first? Is a word with only ever in one class, or do we allow a word to be in multiple? So in this particular example, you actually have it has to be in one class. This is actually, one of the problems with it, right? Like, obviously words have multiple meanings, but in this particular example, you actually, because you're doing a clustering, you actually, I'll show you an example in a little bit. Because you're doing clustering, it's actually just a one-to-one assignment, which is really stupid, obviously. But let me just describe how you're going to actually do this clustering. The way it works is, well, the cute thing to do is you basically start with every single word in its own class, right? That's the extreme thing. If every single word is its own class, then that would basically reproduce your normal frequency thing, right? Basically here, think of, when I say probability of class given W2, that's basically saying I want to match words that are in that class. Well, if the class is only the word itself, then I'm just going to match the word, right? So then this would just reduce to probability of W2 given W1, right? And then probability of W2 given class of W2 is just going to be 1 because that's the only word in my class, okay? So the key point is that if I set every word to its own class, then it reduces to the normal biram model. Then what I'm going to do is I'm going to start merging words together, right? So I have my base example where every word is in its own class. And then this is like that hierarchical clustering thing where you can see, let me just show you what it looks like. It looks a bit like this, right? Every word is in its own class, right? And then I'm going to basically start pushing classes together. How am I going to do this? I'm going to basically merge classes together that give me the smallest reduction in the likelihood of the data, right? So what essentially I'm going to do is I'm going to like look at all possible classes that I can just merge, and then the one that sort of gives me the smallest reduction, because obviously in the extreme, the MLE, I mean, this is the MLE, right? The reason why we're dealing with the MLE is because it's the maximum likelihood estimator, right? So you should think about in your head why the MLE has the greatest likelihood. Why the way we've characterized it using the empirical frequencies corresponds to the MLE. But then what you're going to do is you're going to basically start merging classes together that give you the smallest reduction in the likelihood. And what that actually gets you is actually going to do something that's intuitive. It's actually going to bring words that are somewhat synonymous together so that they're in the same class. Right? And if you can push these words together, then you you're able to sort of be less extreme about when you're matching the words themselves. Okay, so if you actually do this on some corpus, these are some sample merges you see, and these correspond to clusters you will actually get out when you run this algorithm, right? So thankfully, you see that the days of the week is one cluster that you can then basically, the idea is that they're basically interchangeable, right? This doesn't really, it's not surprising, right? This is interchangeable. So if I put them all into one group and I consider them together, then that's not going to matter too much in terms of my likelihood. And so thankfully it does that. Okay, so on Wednesday, we're going to work through why this might not be good and how we can do better in terms of these types of language models. Whew. Any questions?
Quick question.
Yeah.
So wouldn't this clustering method be like grow exponentially in runtime as you increase the number of words?
Um,
Oh, I see. I didn't see the last two.
So, okay. So first of all, usually what you do is you just have a corpus, right? So you just have a corpus, and then you're basically like the V is what matters here, right? So it's not so much. I mean the actual computation like is a little bit tricky. I think I don't know if it's going to be. I think it's not going to be exponential in V. But if I have a fixed set of, if I have my fixed corpus, what I'm going to do is at each time I'm going to look at a potential merge and then recalculate the likelihoods for that particular set. I think there are probably like little computational tricks you can do here. So I don't think it matters too much. Okay, also, like, no one uses this anymore. Like, this is really just an intuition to give you maybe why you might think about sort of like clustering words together. I guess, okay, so as a hint to like what's going to happen next, like these clusters are silly, right? Because, house, roof, abode, like, oh, dog, cat, mouse, they're not really exchangeable, right? They have different meanings. Obviously, in certain circumstances, you can exchange them in a sentence. But actually, you want to be a little bit more like, direct about what you mean by whether or not these things have good clusters or how exchangeable they are. So what we're going to do is actually represent them in terms of vectors, each word, in such a way that maybe the vectors that are close together in their high dimensional space are a cluster, so to speak. So you sort of get the same clustering idea, but you do it through vectors as opposed to like this crude class label.
Right. Okay. So something like A means clustering for words.
Yeah. A little bit. I mean, okay, I'll go through more detail. But the whole point is just like this actually might not be computationally that tractable. It's just in terms of the complexity. Like if you think about the fact that I'm merging words together, that like once I've merged them together, then I don't have an issue anymore.
Okay.
But the actual calculation of the hierarchical clustering, I agree. I think actually can be a little bit complicated.
Thank you.
All right. I guess no more questions. I mean, I'll be here for a little bit. Let me think about the question.
I have a quick question about the number of free parameters and like the joint distribution.
You mean the first few slides? This one?
Yeah. Yeah. Yeah, that one. Yeah. So just to clarify,
Yeah.
So each of these kind of like conditional probabilities is a free parameter, I guess.
Okay.
that-
Well, okay, sorry. So okay, let me just first be a little bit clear. So I'm only talking about this last conditional guy. So I'm literally just talking about like this guy here. I like, what is the number of free parameters for this guy?
Oh, sure. Okay, yeah. So each of the like W1 through Wn minus 1 is a free parameter.
No. So okay. So so intuitively, okay, let's think about what we're doing, right? So what we're trying to do is we're trying to specify. We're trying to specify this distribution, right? And what I'm saying is, how do I specify this distribution in general, right? Sorry. So I want to specify this probability of Wn given W1 to Wn minus 1. And this is just a conditional distribution. The number of parameters in my conditioning thing is like W1 to Wn minus 1. Each of these, because it's a categorical variable, it's V possibilities, right? So really all I'm saying is one way you can think about this is you're just going to basically, okay, let me be even clearer. So suppose V is my vocabulary and there are 3 words, red, blue, and table, right? So there are only 3 possible words, right? So in order for me to entirely express entirely this W1 to Wn, what do I need to do is I just basically need to, okay, well, it doesn't actually help to have the V there. Basically, I need to just write out what's the probability of Wn given, W1 was red, W2 was red, right? Also red, table. Okay, this is a bad example. But the point of this is that like, I'm gonna basically say, I don't actually, the way I can think about this is like, I'm gonna basically set every single possible probability to be a parameter that I need to specify, right? I'm not gonna be smart and like try and be creative about it. I'm just saying, well, what's the worst possible way I could do this? I could set every single probability for every combination of words to be a parameter, right? And so then that would basically mean I would have to characterize like capital V to the power n minus 1 conditional possible histories, right? Right. So what I'm saying is like, yeah, for every possible sequence of words from 1 to n minus 1, I then need to define a probability distribution for the next word. Right?
Yeah,
How many? Oh yeah, sorry.
Oh yeah, so I understand that there are like V to the n minus 1. I guess like different like combinations of words that you can make. I was just a bit confused on where the V minus 1 came from.
Right. Okay. Yeah. Okay. So once I've, all right. So as I said, for every single possible history, once I've fixed a possible history, right, then I need to, given this sequence of words, I want to figure out I want to describe the probability for the next word. How do I describe the probability for the next word? that's going to be a distribution over my vocabulary, right? But in terms of free parameters, I only, intuitively, it seems like I would need V of them, but I only need V minus 1 because once I've described V of them, V minus 1 of them, the last one is is set because it's a probability distribution. So they have to sum up to 1. So that's why like the free parameter is -1, V minus 1.
Okay, that makes sense. Thank you.
Yeah, sorry. Cool. Okay.